I've kept up here the problem that we just did. Wanted to make one note on the notation. You'll notice when I'm describing my region using just one symbol, there's just one differential dA. We're integrating with respect to area. So this is the area of the base, this is the height. Okay. When I have individual limits of integration, I need to have individual differentials because I need to know that these are my y values and these are my x values. So it'll always match. Okay. You'll never see the double integral over r dx dy. If you've got dx dy, you've got to have individual limits for x and for y. Okay. So the region R will go with a dA, individual limits will go with a dy and a dx. And you may very well be wondering, we got this by essentially doing volumes by slicing. So we were working over this region R in the xy plane, and we had sliced things this way. Okay. So we had chopped the interval along the x-axis up so that this dx essentially represented the thickness of each of these slices, and this inside integral was the cross-sectional area we got at a particular x value. So if I picked a representative x value here, and then I'm going to integrate from 0 to 2, but what I'm integrating is the function that I get. Remember, this is assigning a z value or a height to things. So I'd be, the way I've drawn it here, the cross-sectional area would be sticking out from the board. I'd be integrating to calculate that cross-sectional area. Could I have sliced this the other way? Could I have instead chopped things up into horizontal slices so that the thickness of my slice is a small change in y? Then I would have been holding y constant and integrating with respect to x to get my cross-sectional area. Sure, there's nothing that says I have to chop things vertically or horizontally. If I did things this way, my outside integral would be the integral that has me multiplying by the thickness of the slice and adding up the slices. My inside integral would have been the integral with respect to x. That would be finding the cross-sectional area I get if I hold y constant. Makes sense from a geometric perspective that it shouldn't matter whether I chop things into vertical slices or horizontal slices. I'm chopping it up into little pieces, I'm approximating, I'm adding, I'm taking the limit. It should work either way. Let's just real quickly confirm that. Okay. So I would be doing this inside integral first. So x is my variable, y is constant. So we would still have the integral from 0 to 2 dy. That's just sort of my shell. And inside of that, I'm doing this work. So integrating with respect to x, I'm going to get 3x minus x squared over 2 minus xy. Okay. And that's evaluated between 1 and 0. So we've got the integral from 0 to 2 of, when I plug in 1, I'll get 3 minus 1/2 minus y. And when I plug in 0, since there's an x in every term, I just get 0. Okay. So that's the integral from 0 to 2 of 5/2 minus y dy. That would be 5/2 y minus y squared over 2, evaluated between 2 and 0. Okay. So that's going to give me, when I plug in 2, I'll get 5 minus 2 squared over 2 is going to be 2, minus 0, I'm going to get 3. So it did work. And that's actually a very important theorem. It's called Fubini's theorem. So if I have the double integral over r of f of xy dA, where r is this rectangle AB cross CD. Okay. Fubini's theorem says, and I'll write his name down here, Fubini's theorem says that I can do that as an iterated integral and I can slice either way, which means I can integrate in either order. So I could say it's the integral from a to b, the integral from c to d, f of xy dy dx, y is on the inside, x is on the outside, or I could say that's equal to the integral from c to d, integral from a to b, f of xy dx dy. X is the inside integral, y is the outside integral. Okay. So geometrically, this corresponds to I can slice things either way. Algebraically, it says I can integrate in either order. I am deeply indebted to Professor Jensen, whom I had when I was in graduate school. He turned the name Fubini into a verb. So anytime I switch the order of integration, I say I am Fubiniizing. It's a great verb. It's fun to say. Okay. Now, in this particular example, I don't think the problem was easier one way or the other. Didn't really make a difference whether I integrated with respect to x first or with respect to y. But let's just take a look at an example. Let's suppose I have the integral from 0 to 2, integral from 0 to the natural log of 2, let's see, y e to the xy dy dx. So it's given to me as an iterated integral. You'll notice I have individual limits of integration and individual differentials for each variable. Okay. As written, I would be integrating with respect to y first. And I'm not crazy about that because I could try to use an integration by parts, but it's a little bit tricky just because it looks like I would want to be doing some sort of a u substitution here because this is a function composition. Notice what happens if I Fubiniize, if I switch the limits, the order of integration. Okay. I'll have the integral from 0 to natural log of 2, 0 to 2, y e to the xy dx dy. Okay. So notice if I'm switching the order, that switches the limits of integration as well. And here, that's all I need to do because all of these are just numbers. Okay. Now, what's really nice is I don't have a variable in both factors anymore. That y is just a constant when I'm integrating with respect to x. And so this factor, the e to the xy, is what I need to focus on integrating, and that looks like I would want to do a u sub. U would equal x times y. So du, remember I'm treating x as my variable and y as a constant. So the derivative with respect to x of x times y would just be y. So du is y dx. For the purposes of this inside integral, y is just a constant. This is great. Now I've got the integral from 0 to the natural log of 2. That's going to be my dy. So I want to write this inside integral now in terms of u. So u was x times y, where y is a constant. So I'm going to get 0 times y, which is still 0, and then I'm going to get 2 times y. So my limits of integration change there, but then I've just got e to the u du. Fabulous. Okay, so let's come over here to continue. So my shell is the integral from the natural log of, from 0 to the natural log of 2 dy. Inside of that, I'm going to have e to the u evaluated between 2y and 0. So that's the integral from 0 to the natural log of 2 of e to the 2y minus e to the 0 is 1, and then we've got to integrate that with respect to y. Don't forget, when you plug in 0 to the exponential function, it doesn't go away. Very often when you're plugging in 0, if you're plugging into power functions, plugging in 0 makes everything drop out. Exponential functions, it does not. Okay, fabulous. Now, this is a quick u sub that I'm comfortable just doing mentally, and if you're comfortable doing it mentally, you can. I mean, technically, I'm writing out u is equal to 2y, so du is 2 du, But I'm just going to say this is going to give me e to the 2y times a half. Don't forget you do get that extra factor of a half. Minus y, and that's evaluated between the natural log of 2 and 0. So that's going to be 1/2 e to the 2 natural log of 2 minus the natural log of 2. And that's what I get when I plug in natural log of 2. Minus what I get when I plug in 0 is going to be 1/2. Because this will become 1/2 times 1. This term will drop out. Okay. I can definitely simplify that. If I look at e to the 2 ln 2, that's the same as e to the natural log of 2 squared. Because if I'm multiplying in the exponent position, that's a power to a power. Okay. But e to the natural log of 2 is just 2. Squared is 4. So this becomes half of 4, which is 2, minus natural log of 2, minus 1/2. So that's 3/2 minus the natural log of 2. But you noticed how Fubiniizing and switching the order of integration made it a much more doable problem.